Hey everybody, Jeff Oriema here. I've been working on a benchmarking suite to evaluate the token usage profiles of MCP tools hooked up to a GraphQL versus RESTful JSON API backends. I want to share some early progress. This is by no means finished, but I want to show my work and learn along the way. The bottom line up front is that GraphQL over MCP appears more efficient than REST over MCP. Now, I know coming from a very happy GraphQL user, that might not shock you to hear, but I'll dive into the methodology and show my work. Leave a comment if you think anything could be improved. First, I'll show the overall structure. This is all run on Haiku 4.5 currently. When I feel like the suite is closer to being finished, I'll do runs on a more powerful model. But task success has not been an issue so far. That model is called by 4 harnesses, which I've dubbed A1, A2, B, and B2. The A harnesses use REST backends. The B harnesses use GraphQL. I've stubbed out a C harness, but it's not ready to be added to the suite quite yet. Each harness is given an identical set of 2 unique tasks, each of which is consuming GitHub's API. I thought this was a suitable choice for a few reasons. First, it enabled me to use their first-party MCP server for the A tasks. Second, GitHub supports a REST and a GraphQL API. This means that for all conditions, I'm consuming a supported production service deployed by a reputable provider. These are the benefits. Once we dive into the numbers, I'll comment on some drawbacks. GitHub's MCP server does not consume the GraphQL API. So for condition B, I am using Apollo MCP server. This ships with 4 tools out of the box that work on any GraphQL schema: search, introspect, validate, and execute. Condition B2 is using Apollo's Rover CLI. This is not an MCP server, so I created a thin wrapper using Python that exposes 3 tools: schema search, which calls out to Rover schema search; schema describe, which calls Rover schema describe; and GraphQL execute, which executes the GraphQL operations. The 2 tasks being run through each harness are trivial. Task T1 asks for data on 5 pull requests and specifies their IDs. Task T2 asks for properties of 1 specific PR. All of these are tightly scoped, bounded, and as deterministic as possible given how language models work in practice. All inference data is logged via proxy, so I can analyze it later. My previous video on this suite dove into a few cache-busting techniques that helped ensure each test was run with a cold start. Check that out if you're interested. Each task is run 3 times on each harness so that we get a bigger data set, and outliers matter less. Here are the results I'm seeing, and again, this is early. I'm iterating on the suite every week and trying to identify and mitigate bugs and bias. The inference calls for each scenario can be broken down into 3 stages. Stage 1 is schema injection. This is not GraphQL schema. This is MCP tool schema. More tools is equal to more tokens spent on stage 1. GitHub's MCP server exposes more tools than the GraphQL servers. Stage 2 is context growth. This is where the agent accumulates context through tool calls, reasoning, and orchestration. Each of these inference calls results in writing to the cache so that it can be efficiently read when ready for the last stage of inference. Stage 3 is inference compute. This is the last inference call where the agent forms its output, reading from all the tokens that were generated in the previous stages, and sends them to the user. Here are the results I've seen so far. The REST tasks, A1 and A2, spend significantly more tokens loading the schema and making tool calls. Task T1 is the more complex task, and you can see that the greater complexity accentuates the difference between the REST-backed harnesses and the GraphQL-backed harnesses. There are some potential confounders here. I'll get to that in a little while. But I wanted to show you this chart on the right, which I think makes the cleanest case for GraphQL. Tool response size per task. This is a logarithmic scale, and this chart shows the GraphQL over MCP calls consuming an order of magnitude fewer tokens than the REST over MCP calls in aggregate. This is a direct consequence of GraphQL's query language, which allows clients to specify only the fields they need. For mobile and web applications today, this may not be as big a problem with the widespread availability of high bandwidth internet connections. So shipping a mobile app, for example, over GraphQL is more efficient, but that marginal value is not that high. But for agents, every byte over the wire equals more token spend, which is relatively expensive. One last section I'd like to show is some pull quotes from the logs. This document specifies 4 inference patterns. 2 of them are unremarkable and not worth tracking because they're fairly consistent. I'm mentioning them for the sake of completeness. So here they are. The first pattern, which is initialization, and the last pattern, which is synthesis. Initialization encompasses inference calls spent doing cold start, things like tool schema injection, and initial cache write calls. Synthesis is the last stage of inference, which forms the final response to the prompt after all tool calls have been exhausted. Both of these stages are constant conditions over all the different test scenarios. So that leaves 2 highly differentiable inference patterns: orchestration and reasoning. Orchestration is the process of coordinating tool calls and iterating over data in context. Reasoning is compositional. It encompasses tokens dedicated toward selecting and interpreting data. Both are equally costly, but reasoning is higher value. This document quotes examples from the suite and attempts to categorize these inference calls. You can see that the rest over MCP runs are more procedure-heavy, favoring orchestration-type patterns. The GraphQL over MCP runs are more reasoning-heavy, dedicating tokens to query composition and field selection. One caveat apparent in this data is that the model's pre-training data contains the GitHub GraphQL schema. I'm not sure whether that counts as a compounder, because on the one hand, that removes the need to make at least one potentially expensive tool call. But pre-training data should also have GitHub's MCP server and REST API structure included as well. And it's not clear whether using a novel schema would be meaningfully different if we vectorized it, but it's something I intend to dive deeper into, so we won't leave it there. As for next steps, I hope to try more complex tasks that span multiple services. I have a hunch that the efficiency gap will actually widen when using a federated graph, which gets orchestrated at the router level rather than at the much more expensive agent level. We'll see what the numbers say. That's it for now. See you next time.